The formation of an electrochemical double layer around a particle is explained as follows. If a particle of a size greater than 1 nanometer is dispersed in water, there will be a reaction at the solid-liquid interface. Both parts, the solid and the liquid part, carry different energy levels, which lead to a tension at their interface once they get into close contact. Basically, all substances intrinsically carry a negative surface charge once they are dispersed in water. This is caused by the high dielectric constant of water. Generally speaking, media with a lower dielectric constant carry an anionic surface charge. Water contains ions of dissolved salts. Attracted by the surface charge, these ions gather around the particle. A well-ordered and immovable layer covers the surface of the particle like a skin. This layer is also called the stationary layer, or Stern layer. Cationic ions neutralize the anionic surface charge. However, as ions are often surrounded by water molecules, they are rather big and cannot neutralize the surface charge completely. A residual anionic charge remains. This remaining anionic charge attracts further ions from the surrounding water, so that a second layer develops around the particle. This layer is further away from the particle's surface. The attractive force of the anionic charges get weaker with the distance, and therefore this second layer is less ordered and movable. The second layer is called diffuse layer or Gouy-Chapman layer, and is colloquially often termed cloud of counterions. The boundary line between the stationary and the diffuse ions is a shear plane. The potential at this boundary line is called Stern potential or streaming potential. If the diffuse ions are displaced from the particle they surround, a potential difference is created and can be measured.
What happens when a charged particle is immersed in a liquid such as an aqueous electrolyte solution? In this case, there's a positively charged particle surface, and somewhere there has to be a balancing negative charge. Typically, that will be in the form of ions adsorbed onto the surface of the particle. And you can consider this to be a fixed or rigid layer of charged material. With an electrolyte solution, there's a uniform distribution of anions and cations in the bulk. Near the particle, anions, shown in yellow, will be attracted towards the particle, leading to a higher concentration of anions. And similarly, repulsion of cations, shown in blue, will result in a lower concentration of cations. This region is a diffuse layer of ions, balancing the charge on the particle. So we have a rigid layer associated with the particle surface and tightly bound material, and then a diffuse layer. And combined, we get the diffuse electrical double layer. There's a transition from the diffuse layer with an excess of counterions to the bulk solution with a uniform concentration of ions. Very close to the particle, material is either adsorbed or strongly associated with the particle, such that it remains with the particle when it moves relative to the liquid. The transition point between bound and free liquid is called the shear or slipping plane. But what does this say about the magnitude of the electrostatic repulsion between particles? If we have two such particles approaching, we know intuitively that there'll be electrostatic repulsion. But how is that quantified? And how does it look spatially as you go away from the particle? I'm going to superimpose on the schematic of the double layer a graph of electrical potential as a function of distance away from the particle surface. Electrical potential is something that's not usually described very well when explaining the double layer. But the concept's fairly straightforward. If you have a charged particle carrying, say, 100 elemental charges and a single elemental charge of the same sign infinitely far away, and you want to bring that unit charge up to where the particle is, then you have to provide energy. This is electrical potential energy and is expressed as a voltage. So the electrical potential is a measure of how much energy it takes to move a single point charge to the particle from infinitely far away. It's an indicator of the repulsion that's going to exist between particles as a function of their separation. So that's the connection between charge and potential. If we look at this diagram, then we have a starting potential at the surface, which is psi sub 0. The surface charge is screened by the presence of adsorbed material of opposite charge, so the potential decreases between the particle surface and the slipping plane. The potential at the slipping plane is defined as the zeta potential. The potential continues to decrease beyond the slipping plane due to the electrolyte and polar nature of the liquid. The distance over which it decreases depends on a number of factors. A thickness is defined as the distance at which the potential has decayed to 1 over E of its initial value. And this distance is written as 1 over kappa. Let's look at the effect of different electrolyte concentrations on the thickness. On the top left, we have a dilute electrolyte. The decay is slow. At the highest salt concentration, shown on the bottom right, the double layer thickness is very thin compared to the most dilute salt concentration. Here are all of those decays on a single chart, including markers to represent the thickness of the double layers. For an aqueous solution at room temperature, kappa is given by this equation. I is the ionic strength and is a measure of the concentration of all of the ionic species present, taking into account their valencies, since polyvalent ions are more effective at screening than monovalent ones. So you can see that as you increase the ionic strength, the double layer becomes thinner. And when it's very thin, it's said to be collapsed. So this represents repulsion between particles. How does that fit into the overall picture of colloidal interaction, where you have attraction as well as repulsion? According to the DLVO theory, you can add the inherent attractive potential energy, shown in blue, and the repulsive potential energy, in orange, to get the overall interaction energy, shown in grey. Here, there is an energy barrier that prevents aggregation. Let's look at the 4 different salt concentrations. The energy barrier becomes smaller as you increase the salt concentration. By the time you get to the highest salt concentration, there is no barrier and the particles will aggregate. But it's not sufficient to refer to just the zeta potential to indicate the aggregation behavior of the system. I've assumed in these graphs that the zeta potential is the same. Yet if you increase the salt concentration enough, you will induce aggregation. So the rule of thumb that people use, that if zeta is greater than 25 millivolts, then the dispersion will not aggregate, can be very misleading and affect your interpretation of measured zeta potentials. You have to take into account the ionic strength, and you have to have some reasonable idea of the attraction. There's not much you can do about attraction in a dispersion. The 2 main factors which affect the attraction are the size of the particles and their optical properties. But you can control the electrostatic behavior through choice of electrolyte concentrations and addition of ionic surfactants, for example. How can we access the zeta potential? What phenomenon can we exploit to provide us with some way of measuring the zeta potential? The most common is electrophoresis, which is the motion of a charged particle in an electric field. If you apply an electric field using two electrodes, then a particle will move towards the oppositely charged electrode, and there'll be a balance between the force trying to move it towards the electrode, the electrostatic force, and the friction force due to the viscosity of the liquid. The resulting terminal velocity will be proportional to the electric field, and the proportionality constant is called the electrophoretic mobility, mu. At the same time, the diffuse layer of ions around the particle will try to move in the opposite direction, towards the other electrode. Clearly, there's going to be some kind of balance between the two. Here's a schematic of a particle whose radius is A with a thick double layer. So 1 over kappa is large, which means kappa is small, and the ratio of the particle radius to the thickness of the double layer is simply kappa A. For small kappa A, the Huckel equation relates the electrophoretic mobility to the zeta potential. Epsilon sub r is the dielectric constant of the liquid, and eta is the viscosity. You may be familiar with the Huckel equation, depending on which instrument you use. The other extreme is a very thin double layer, and the Smoluchowski equation is used. It's similar to the Huckel equation, but without the factor of 2/3. Intuitively, that makes sense. You don't have the large cloud of ions slowing the particle. So for a given electric field and zeta potential, the particle will move faster. Then there's the in-between situation, where the particle radius and the thickness of the diffuse layer are comparable. Somehow, we need to go from 2/3 to 1, to go from the Huckel model to the Smoluchowski model. We can write the equation with a multiplier that is a function of kappa A. This was first considered by Henry in the 1930s. And one of his functions looks like this. There's at least one instrument that incorporates this calculation of zeta potential from mobility. The advent of digital computing and powerful numerical analysis has allowed more rigorous models to be developed that look something like these calculated by Overbeck. The choice of model depends on the type of electrolyte and the zeta potential itself. There's quite a discrepancy when you're in the middle region of kappa A. You can see that in this region, the calculated zeta potential will be underestimated if you use the Huckel, Henry, or Smoluchowski equations. So how does that tie in with the real world? Because kappa A relates to the ionic strength and the particle size, then we can look at a realistic range of salt concentrations and a realistic range of particle sizes to see just where we'd expect to get significant underestimation of the zeta potential. Here we see the electrolyte concentration tabulated against the particle radius. The pink color shows where we'd expect significant deviation from the models that commercial instruments provide. And it's pretty much most of the real world. And I haven't even touched on measuring the mobility and the assumptions that go along with that. So let's look at electrophoretic light scattering. If we shine a laser beam through a sample of particles, each particle will scatter the light and create a Doppler shift dependent on the velocity of that particle. It's like a police radar speed trap. And if you have millions of particles, then you have millions of Doppler shifts all contributing to the intensity of the scattered light. This varies with time in a similar way to a sound signal. You can use a spectrum analyzer to see the frequency components of the sound, and you can do the same thing to see a spectrum or distribution of the Doppler shift frequencies of the scattered light. If you know the geometry of the equipment, you can convert the frequency distribution to a velocity. distribution. If you know the electric field, you can get an electrophoretic mobility distribution and then calculate a zeta potential distribution. This has been available since the 1970s, and here we see a zeta potential distribution. Another method is phase analysis light scattering, PALS, that I invented in the late 1980s. It uses a different way of processing the same signal. Why would you want to do this? Well, the laser Doppler method has a limitation as far as how much electrolyte you can have present in your sample. As you increase the electrolyte concentration, you start to see adverse effects like heating or bubble formation at the surfaces of the electrodes and other unwanted behavior that makes the measurement impossible using the laser Doppler method. Phase analysis gets around some of the limitations, but sacrifices the ability to show you the distribution. Instead, you get a single average value. Above 10 millimolar ionic strength, commercial instruments switched to using PALS, simply because they cannot do the laser Doppler measurements. But PALS measurements are only valid if the sample is truly monomodal with respect to zeta potential. You have to assess whether that's an appropriate assumption or not for your particular purpose. I've developed a next-generation electrophoretic light scattering system that does allow you to get the zeta potential distribution at these higher electrolyte concentrations. But there's another problem that arises with using high salt concentrations, and it also relates to the electrodes. When you put the voltage across the electrodes, each electrode assumes a charge. On the left, we've got a positively charged electrode surface, and it looks just like the surface of a positively charged particle. There's a double layer, and there's a daubed material. If you look at the electrical potential curve, you see the same drop across that bound region. The potential within the sample is less than you're assuming it to be just based on the distance between the electrodes and the voltage. Even though there are different ways of generating the electric field with different instruments, they don't account for this drop in the electric field. So calculated zeta potentials are underestimated. So we have underestimation of zeta potential due to electrode polarization, and underestimation due to the wrong choice of model to do the calculation. That's two assumptions that lower the calculated zeta potential. My new instrument can determine what the true electric field is and make a more faithful measurement that will increase your confidence. I've collaborated with the University of Sheffield to compare my next generation system with a leading commercial instrument. We studied electrosterically stabilized latex particles in potassium chloride solutions ranging from 0.5 millimolar to 4 molar. The blue data are from my instrument, and the red data are from the commercial instrument. Not surprisingly, the instruments agree up to 10 millimolar. But beyond that, the commercial instrument reports a lower zeta potential than my instrument, which accounts for the reduction in the electric field.